Well, the last day we learnt about two measures of dimension. One, the box counting dimension, and two, the correlation dimension. These are things to characterize a chaotic orbit, also to distinguish between a non-chaotic orbit with a chaotic orbit. But then we have already learned, while we were talking about the continuous time dynamical systems, that one way to characterize chaos is through the exponential separation of nearby trajectories. That means sensitive dependence on initial condition. The two measures that I have already talked about, they do not quantify exactly the sensitive dependence on initial condition. They sort of quantify how distributed are the points of the orbit. But then there is another measure of chaotic orbit that quantifies the sensitive dependence on initial condition, and you have learned that that is called Lyapunov exponent. What was it? What was the concept? Central concept then, that if you take 2 points very close to each other, then if the system is chaotic, then one would evolve like this, the other would exponentially diverge from it. So the two will evolve in two different ways. They will not keep hand to hand with each other, and the separation therefore will increase. That is what we learnt at that time. Now we are trying to port the same idea in discrete time. Earlier it was a continuous time concept. Now we are trying to port the same idea in discrete time. Well, in the discrete time also, then we will have to talk about two very nearby points and how their separation explodes. Of course, here also we need to keep track of the fact that even though their separation diverges, really the separation between them do not go to infinity. Why? Because overall the orbit is within a definite boundary, because the chaotic orbit is always bounded. If both the points are bounded, then mutual distance also cannot grow infinitely. So obviously we have to keep track of the issue that their mutual separation is increasing exponentially, but at the same time that cannot go to infinity, so that there are also folds. Now when we consider maps, essentially we will again talk about a point, say x naught, and another point, say x naught plus some small number epsilon. And then in the next iterate, if you apply the map to both these points, then they will map to two different places, and their separation is expected to increase. Okay. So here was the separation between the 2 points, and that is what it becomes when you apply it one iterate. And if you keep on applying that, this separation will it keep on increasing? No, obviously not, because after some time they will be it cannot indefinitely increase, of course. So we can say that if you have the distance between x naught and x naught plus epsilon to begin with, and that becomes the distance between these two, f x naught and f x naught plus epsilon. So this distance maps to this distance, and we wanted to say that this d of f x naught comma f x naught plus epsilon, this fellow is the initial separation times e to the power lambda. So e to the power, this is exponential separation. We are talking about exponential increase in separation. So e to the power lambda times I'll say what it is, times d to the power d of x naught x naught plus epsilon. If you take say 2 iterates, then we might say twice iterated, and then we would say okay, if it is n iterated, so we would say right. So essentially then you get your lambda as, how do you extract lambda from here? This is n, 1 by n, 1 by n, it is the d of f n x naught, f n x naught plus epsilon divided by this fellow. This fellow is nothing but epsilon, right? The distance, yes, ln is here. Okay. So this would be the concept of the Lyapunov exponent.
So why should it be e to the power lambda and not just lambda?
Here,
Because the exponential term was coming because it was a dx by x.
it is a, we are assuming that the 2 points, their separation increases and that increases exponentially. You might question, why do you assume that it is exponentially increasing? You might, it might increase any other way, but it is just an assumption, that we assume that it is exponentially increasing. If that be so, then the experiment is that. Now you would realize that even though the essential concept is that, it is not so easy to actually measure it. Why? Because this distance, if you keep on iterating, then the distance is no longer really going apart. So you need to do something more, something else to it. Essentially what we do is, since we have to take the nth iterate, we have to take the nth iterate of x naught as well as the moved one, x naught plus epsilon, nth iterate, and essentially what is happening, we are looking at how the nearby regions expand. So from one point you take one step and you see how it expands, then you take the next step, you see how it expands, then you take the next steps, you see how it expands, and then the rate of expansion averaged over the whole orbit is nothing but this. Okay. So what you are really looking for is the averaged rate of expansion. Now the direction of expansion is different in every place. As you go on from one point to the other, the direction of expansion is different. So you can look at it this way, that suppose an orbit is going like this, and so on and so forth. That means starting from x naught, it is going through these set of points, iterates. Then if we locally linearize around that and obtain the Jacobian matrix, then that Jacobian matrix, its eigenvalues will tell me how a particular direction will expand. Go to the next point, do the same thing, you will get again a Jacobian matrix, but the eigen directions in all those places will be different, so that they will be shifting, moving, but nevertheless at every place you can find the expanding direction. Averaged over the whole, you get the Lyapunov exponent. Clear? Averaged over the whole, you get the not exponent, Lyapunov number. I will come to that. So essentially you can then, since you can say that the derivative here what am I doing? Here I am taking the derivative of the nth iterate. For example, we have taken the second iterate of some map, the third iterate of some map, and taken the derivative. It is like that. Taking the derivative divided by the initial separation. Taking the derivatives at the two places. But by chain rule, we can say that the derivative of the nth iterate is nothing but the derivative of at this point times the derivative at this point times the derivative at this point, and so on and so forth, and then we can divide by n to get the average. Doable procedure. So, in general, we define the Lyapunov number or the average rate of expansion that way. Clear? Now, let us bring back the concept that if you have a point and you have obtained the Jacobian matrix at that point, then essentially at this particular point you would be writing that x naught is the point, say, applied on it you have to say that the Jacobian, that means it is often written as df of x naught, f x naught, df is the Jacobian of x naught, right. If you apply this, and if you apply not only to the point but also to a circle around it, what have you? You get an ellipse. We have already said that. So, you actually get an ellipse. Somewhere else it falls as an ellipse. The point maps to a point somewhere here, but the region around it maps as an ellipse. And we have already seen that the major axis of this ellipse and the minor axis of this ellipse are given by the eigenvectors of this matrix times its transpose. Okay, we have already seen that. So, you might argue that we can keep on obtaining this and multiplying this. Yes, that might be a procedure. That might be a procedure, provided you are able to obtain the sequence of points, take Jacobian around them, and apply this procedure. It is possible. Now, if you can do that, then the definition of Lyapunov number and exponent would be as follows. Let write down this definition, because that will be followed in the later classes. Let f be a smooth map on a m dimensional space, real space. What is the meaning of the term smooth map? It is differentiable everywhere. That is all. Smooth means differentiable everywhere. Let Jn So, these are the Jacobian matrices, okay, and k varies from 1 to m, and let R n k the longest. So, this is the longest orthogonal axis that you obtain out of it, of the ellipsoid. Normally, it will be ellipsoid. If it is 2D, then we will say it is an ellipse, but normally it will be an ellipsoid, m dimensional ellipsoid. Jn n for an orbit So, V0 is the initial point. We have applied the Jacobian, we have obtained the Jacobian of the nth iterate of that is called Jn. R after that, after we have obtained that, then the longest orthogonal axis is R n k. What is k and what is n? K is the dimension, it measures the dimension. If it is a 3-dimensional system, then obviously there will be 3 directions in which we will measure. The ellipsoid will have 3 axes, and this is the longest axis of that. That is all. Then, sorry, smaller. Then R n k measures the contraction or expansion near the orbit V0 Okay. Notice what you have done. We have started from a point V0. We wanted to find out how it expands or contracts, the region around it expands or contracts after n iterates. So, what we did? We obtained the nth iterate of the map, obtained the Jacobian of that map, the nth iterate map, and from there we obtained the major axis and the minor axis of the ellipse, and we call this the major axis. Okay. If this is the major axis, that will measure the expansion or contraction. Clear? So, we are essentially at this stage avoiding the question of changing of the dimension, because we have already taken the nth iterate. So, that contains within it all the changes and stuff. So, that will measure the contraction or expansion near that orbit starting from V0 in the next n iterations. Then the Lyapunov number of the point V0 is defined as limit okay. So, if in n iterations it increases by so much, in one iteration on an average how much does it increase? To the power 1 by n. That is why this term is needed. So, this sort of gives my average rate of expansion, but that is not Lyapunov exponent, because the Lyapunov exponent is an exponent. So, e to the power exponential factor has to come in. That is why this is not called the Lyapunov exponent, this is called the Lyapunov number. Is that clear now? So, this is the Lyapunov exponent.
Sir, we are utilizing the chain rule here, right?
Yes. As yet no. As yet we have said that suppose we are able to somehow derive the nth iterate of the map, and then the Lyapunov number is given by this, and then we will say that n goes to infinity. Obviously, you might ask, how do you really derive the nth iterate? and then let n go to infinity. We will treat those issues later, but this is the definition. Conceptually you need to understand it, and then this is the Lyapunov number provided this limit exists.
So what is capital N?
Oh. Here around V naught we have taken a circle or sphere, n dimensional sphere, that is called. So if you apply Jn on n, then you get an ellipsoid.
A is that n-dimensional sphere.
Yes.
Sir, n can be written as dv0 then. Capital N.
No. Capital N is the n dimensional sphere around V0. Okay. So around V0 you take unit directions in all the directions, and then whatever that defines is the starting ball n. Fine.
So why are you saying then RKN measures the contraction? Why, if it's the longest?
Well, it might be so that it measures it is something like it might be as well smaller than the initial sphere. In that case we don't have chaos, but nevertheless we have the number, right? Fine. It might be contraction, it might be expansion. If it expands, then only we will say the system is chaotic. But in a general system it could as well be contractive, it will be stable, that is all. Now then the kth now exponent of V0 is, we say Hk is equal to ln of the Lyapunov exponent is nothing but the natural logarithm of the Lyapunov number. Okay, Lyapunov exponent is nothing but the natural logarithm of the Lyapunov number. So far so good, but as yet we have not addressed the question that he was asking, how actually do you do it? How actually we do it is a somewhat different ball game. I will come to that, but essential point should be understood. Is that clear? That the concept is that we take n iterations and then we have a map. So if that is applied on some point V0, some ball around it n, around V0 we get a ellipsoid. The longest axis of that ellipsoid is essentially giving my expansion or contraction or whatever. If it is smaller, it is contraction. If it is longer, then it is expansion. So the extent by which it expands, it is the Lyapunov number. Take the natural logarithm of that, you get the Lyapunov exponent.
So, even though the kth Lyapunov exponent of V0 is Hk ln, I mean it's of V0 or it's of the system?
Yes, here is the question. We have started from the point V0. If it is a typical initial condition, then it is the typical initial condition. What does it mean? I will come to that. Then it is the Lyapunov exponent of the system. But consider that there is a chaotic orbit and there is another stable periodic orbit with a basin boundary separating them. Then what is the typical initial condition? Start from here, you get something. Start from here, you get something else. Right. So naturally we have to say that starting from here I got this, but supposing there is a unique chaotic attractor in the system, then every point is as good. Well, no, not really, because you know that within the chaotic orbit there are a large number of unstable periodic orbits. If you are stationed on the unstable periodic orbit, you will forever remain on the unstable periodic orbit, and that fellow is periodic. So there are those atypical initial conditions within the system. If you start from there, you don't really get the right Lyapunov exponent. So you have to start from a typical initial condition to get the proper Lyapunov exponent. Okay. That is why it is dependent on V naught. Starting from a initial condition somewhere here, you will measure something else. You might say that, okay, if I know the system's definition, then I might as well compute this and say I might as well obtain the long axis, short axis by simply obtaining the eigenvectors and eigenvalues of A transpose. We have already seen that we can do that, but that will be a little bit cumbersome procedure. Nth iterate, it will be even more cumbersome. So, actually it is not done that way. Conceptually it is that, but actually it is not done that way. But since we can keep on applying, the chain rule and apply at each point and obtain, therefore, there are some simple systems on which you can apply this concept. For example, if I tell you what will be the Lyapunov exponent of this map, can you say? Imagine that this slope is 3 by 2 and this slope is 3 by 2. It's not smooth, all right, but smoothness is not all that important. Smoothness becomes important only in situations where I take a point and then if you take a error ball, they map differently. But suppose you take initial condition somewhere here, then can you say what will be the Lyapunov exponent of this fellow? At every iterate, it will expand by 3 by 2 wherever it falls. So, even if you say it is nth iterate, the slope should always be this. Okay. So, for such systems, using that concept, it is possible to obtain the Lyapunov exponent straight away. But in general, when you have to really compute it, that does not really help much. So, in that case, we take a little different procedure. So, we have to essentially start from a unit ball n around the initial condition, and then we have to keep on those matrices. So, essentially what we will do, we will say df of V naught applied on n first, then we have to apply df of V1, so on and so forth, df of okay. All these matrices applied on n should ultimately give me the matrix that I want, and its major axis minor axis has to be obtained. That is the essential problem. Okay. So, if you start from a standard error ball, and then in the first one it lands somewhere here, in the second one say it lands like this, in the third one say it goes. So, it sort of goes on expanding. If there is expanding direction in n iterations, you can expect it to be very long and very thin something, still ellipsoid, all right, but nevertheless very long, very thin something.
So you are not allowing to fold.
It will of course fold. So, that is another problem we have to keep track of. If we do not consider folding, it will become a very long ellipsoid, and if we allow folding, then it will fold. So, that gives us some problem in actual computation. What we will do? We will keep track of the change in one iteration. In one iteration, we do not expect any folding. In one iteration, so a circle, a sphere, a spheroid will go into a ellipsoid, and there can you obtain the major and minor axis? Can you obtain the major and minor axis? Of course, you simply apply, you have the system definition in your hand, that means you have the system model. At this point you obtain the Jacobian, you got a matrix, and that matrices the eigenvectors and eigenvalues will give you the expand and contracting directions. If you want to exactly obtain the spheroid, all that you need to do is to obtain the Jacobian of obtain the eigenvalues of A transpose, that is all. But if you want to simply obtain that from this by one application of V naught, obviously you do not get the right, you get a ellipse, all right, but you do not directly get the major and minor axis, that we have already talked about. So something needs to be done in order to orient our coordinate. Say this was the coordinate, now the coordinate has to be transformed in such a way that one coordinate is this, another coordinate is that, then we can keep track of how this coordinate, the expanding coordinate, changes to this one, right. So what we will essentially do is, how many of you have attended some course on functional analysis, Gram-Schmidt orthonormalization? You have done? You have done. Has anybody else done? No. Oh, that is the issue then. Yeah, because I was anticipating people have done, but then done but don't remember is the most the average over the class, that is the concept. Okay, then we will do this. Suppose I have defined a sphere. Suppose I have defined a sphere with conjugate vectors, let us say Z1, Z2, Z3 unit vectors. Defined by that is my sphere. Now each one then will either expand or contract, ultimately giving a coordinate system that will not be exactly this, it will be something like this as a result of the transformation. Fine. We need to find out where is the major direction, and then we need to re-orthogonalize so that we get back the sphere to take the next step. All right. So the procedure for that is essentially we define a new coordinate system here, y's, that means y1, y2, y3, such that y1 is z1. That means the first coordinate we keep as it is, and the other ones have moved in angle. So we need to somehow bring them back to orthogonal directions. So the way it is done is y2 is z2 minus z2 dot y1 by y1, this is the norm square, times y1. y3 is equal to z3 minus, here it is z3 y1 by the norm of y1 square times y1 minus z3 times y2 norm of y2 square times y2, and so on and so forth. What exactly are we doing? We are saying first that whatever we took as the first coordinate, let it be retained. Second coordinate, now it has moved, and therefore it will now have a component, a projection on the first coordinate, and we need to subtract it out so that we turn the axis back to orthonormal coordinates. That is exactly what it is doing. From Z2, we are subtracting the amount that is actually the projection onto that, as a result of which you get the again orthonormal coordinates. The third one is the third coordinate Z3. Now this will have some projection on the plane formed by y1 and y2, and this fellow has to be orthogonal to y1 and y2, and therefore whatever is the projection on that will subtract, so on and so forth. That is called Gram-Schmidt orthogonalization procedure. Okay, clear? So if we start from a ball, then after every iteration we need to apply this orthogonalization procedure, so that we always keep the axes orthogonal to each other. Else what will happen? They will axes will become unmanageable. Some will expand, some will contract and become distorted in every possible directions. So this is how we tackle the problem of turning. At every stage we are re-orthogonalizing the coordinates. Okay. Then the issue is that every stage, then suppose it was Z1, Z2, Z3, and it has turned into, now we have orthogonalized and we have turned into but now y1, y2, y3 are of the not of the same size. Why? Because some directions have expanded, some directions have contracted. So essentially you will not get this, you will get something like this. Right? Fine. You still have a set of orthogonal coordinates and you can keep on applying it, but that will be inconvenient. Why? Because then this will lead to very small numbers and this will lead to very large numbers after n iterations. And as you know, in computer science it is a very established fact that if you are having to deal with numbers of entirely different orders of magnitude in a same computational procedure, then it is likely to end up in errors. So we always like to operate, do all sorts of numerical operation with same or close to each other size of the numbers. Here we have a problem there. If in one iteration is going to look like this, after say 30 iterations, one is going to be very, very long, and the number that you have to handle maybe 10 to the power 4 or something, and the other one maybe 10 to the power -3 or something. Very inconvenient to handle in a computational procedure. So what is really done is that after every stage you not only orthogonalize but also renormalize. That means you divide again to bring it in a circle shape or sphere shape. So in order to do the renormalization, we say that now the new set of, there will be new set of coordinates Wi, which is yi divided by the norm of, so that it again becomes a unit vector, but the directions are set according to this. Okay, but the directions are set according to this. So what are we doing? We are saying that we start from a point with a ball around it. After first iteration it became a, so naturally we had a long axis. I am drawing in 2D so that it becomes clear to you, but it could as well be 3D or 4D. In this case the two coordinate systems are like this, but that turned into this. Then we say that no, if it becomes like this, in the first iteration we have a measure of Lyapunov exponent, that is this axis divided by this axis. But in order to take the next step, we have to again define a circle around it. In order to do that, whatever was the actual size, we divide by the magnitude to get again a unit vector. So now the unit vector Wi is this vector, and the orthogonal to it and the orthogonal to it. Next iterate it might again turn like this, so that here you will obtain this unit vector, again you will obtain, again you will obtain, and then you will. Having done that, you would say what measures then the growth in one step? It was initially y I n that went into here, it is y I n, y there has been a growth or decay in the size as we have measured here, growth in the decay in the size, and that measured the expansion or contraction in that particular iterate. So, ultimately we can say the Lyapunov number is given by simply the average of in the first iteration whatever was the expansion, second iteration whatever was the expansion, third iteration whatever was the expansion, that is the total thing. That is the Lyapunov number. Exponent is firstly you have to take the ln norm of n plus all these put together divided by okay. So, that is a computationally realizable, easily realizable procedure for obtaining the Lyapunov exponent. What exactly did we do? We started from initial condition, took one step. At that point we locally linearize it, took the Jacobian, obtained the eigen vectors, and thereby we obtain the expanding and contracting direction. When we have obtained the expanding and contracting directions, we take the maximum expanding direction, and then maximum expanding direction longest, that means it is the big axis of that, and then renormalize it and changed all the other axes as orthogonal to that axis. Is that clear? So, the maximum expanding direction is retained as the principal axis, axis 1. Again you may make a sphere, again you take the next iterate, do the same procedure. In every particular iterate, particular jump, you have some expansion of that principal axis. This taken logarithm averaged over the whole thing gives you the Lyapunov exponent. Essential procedure. You might say that there are different situations where I may not have the map in hand. For example, if you have the Henon map in hand, there you have the expression for the map, and therefore at every point wherever it lands you can take the Jacobian, you can do this procedure, no problem, and therefore I would advise you to really try that once. But supposing you have got a continuous time dynamical system which goes on like this, and you have taken a Poincare section and you are obtaining the crossings, you have got only a collection of points, you really do not have a map. How do you take the Jacobian? You cannot do that, you cannot take the Jacobian really. In that case the same procedure has to be followed. By the way, while I was talking about the continuous time dynamical system and the Lyapunov exponent, did I tell you how to obtain that from experimental data? Huh? Okay, let me just repeat that once again. In continuous time dynamical system, what is the procedure? You have got starting from one initial condition, we got one trajectory. From another initial condition, you got another trajectory. So, but if you have the data set, then you do not have this. Huh? Any question? Yeah. If you have the equations, then you can start from a different initial condition, see how it evolves. If you have a data set only, you don't. Then what do you do? Simple. After all, if it is a chaotic orbit, it is winding on, and if the orbit is ergodic, it will eventually visit a close neighborhood of that initial condition. That means while going on, sometime it will come here or some place within a close neighborhood of this. The moment you have detected it, you know how it evolved next, because you already have the evolution of that, right. So, you have very closely spaced data acquisition results here, you also have the closely spaced data acquisition results here. So, you know how it evolves. After some time, again you stop it, renormalize it to this distance, and then again scan the data set to find another point which is within the circle, and go on. In case of the map also, you do essentially the same thing. So, starting from an initial condition, you will go on evolving. In case of that kind of systems where you do not have the map explicitly, that means starting from initial condition, go on evolving, you get a point. Again, ultimately you get a sequence of points, large number of points, a data set. In that data set, what are you looking for? You are looking for, starting from an initial condition, I have to define an error ball. You cannot define an error ball, but you can define a point on the error ball, within the error ball. So, starting from initial condition, simply search the data set to find out another point that lies within that one, and then you know where it jumped next, you know where it jumped, this fellow jumped next. You can find this distance. So, from this distance and this distance, you can find at least the initial estimate of the Lyapunov exponent. Then again stop here and again define an error ball, search the data set to find another point on this error ball, go on doing this procedure. That is how the Lyapunov exponent is actually defined. Now, notice what will be the Lyapunov exponent be if the system is periodic? If the system is periodic, what will the Lyapunov exponent be? 0, no. Lyapunov number, its natural logarithm is the Lyapunov exponent. Okay. All right. So what do you expect the Lyapunov exponent to be in case of a periodic orbit? Negative. Okay. The Lyapunov exponent will be negative. The Lyapunov number would be, yes. Okay. So, Lyapunov number, the extent by which it stretches or squeezes, that should be less than 1, and as a result of which the Lyapunov exponent will be negative. In a chaotic system, what do you expect? In a chaotic system, there has to be stretching in some direction. That is the signature of chaos. Otherwise, you cannot have the sensitive dependence on initial condition. In order to do that, what is the necessity? That at least one Lyapunov exponent should be positive. So, that is the ultimate signature of chaos. If it is chaotic, at least one Lyapunov exponent should be positive. Normally, a system is, the kind of system that engineers have to handle, they are all dissipative systems. There is always dissipation. Dissipation means if you start from error ball, after some time its size will reduce. its size will reduce, but then its size means its volume will reduce, but at least in one direction it will be expanding. That is the character of chaotic orbit. Fine. There are some very rare situations where there are two directions in which the Lyapunov exponent will be positive. Very rare, but there exist such systems where two directions are positive. They are called hyperchaotic systems. They are called hyperchaotic systems. So, in a periodic system, periodic orbit, the Lyapunov exponent will be negative, largest Lyapunov exponent will be negative. Essentially, what really matters is not all the Lyapunov exponents, but the largest Lyapunov exponent. If the largest Lyapunov exponent is negative, then you have contractive system, and in contractive system means you have periodic orbit. If the largest Lyapunov exponent is positive, it is a chaotic system or an unstable system. There also unstable system means it goes to infinity, but nevertheless, if you measure, do this procedure, then it will yield a Lyapunov exponent that is large, but it goes to infinity means is unbounded. Therefore, we leave it out of our attention right now. What if the Lyapunov exponent is 0? What kind of situation is that? Yes. The Lyapunov exponent 0 means two initial conditions will always remain the same distance apart. That is the meaning, physical meaning of the concept Lyapunov exponent 0, same distance apart. Now, while talking about quasi periodicity, I have already done that, right? That this is evolution on a torus. So, you have a torus orbit, and if it starts from another initial condition, it also goes the same way, and their relative distance does not increase. So, that is the situation where you have 0 Lyapunov exponent. At least one Lyapunov exponent being identically 0 means it is a movement on a torus. Okay. Okay. So, I will stop now. We will continue from here in the next class. Torus.